Welcome to another episode of the Mapscaping Podcast. My name is Daniel and this is a podcast for the Geospatial community. My guest on the show today is Dominik Weckmüller, a researcher at the Technical University of Dresden in Germany, and today we're talking about semantic search. One of the keys to understanding semantic search, at least in terms of this podcast and this conversation, is understanding the idea of embeddings. You might have heard of this before. You might also have heard of people refer to them as vector representations. We spent quite a bit of time on this topic during this conversation because it is so important and because it's so relevant to understanding AI in general. I don't have a sponsor for this week's episode, so I thought I'd use this time to mention a project that I'm working on. It's called Quick Map Tools. So quickmaptools.com is the place you can find it. And the idea here is to build out a set of helpful browser-based map tools. It's still very much a work in progress, but if you do take time to check it out, I would love some feedback. Hi, Dominik. Welcome to the podcast. It's a pleasure to have you here. I met you a couple of years ago at the Phosphor-G conference in Florence, and you had this really exciting story. You were talking to me about semantic search. You were talking about something called hyperloglog. You were talking about scraping a lot of data from social media and doing this interesting analysis with it. And I know that your project has matured since last time we spoke. And today, I want to know more about semantic search. I want to know more about something called transformers.js, data embeddings, chunking strategies, and the list is long. But let's start with a brief introduction. Could you just introduce yourself for the audience, please? Who are you? What do you do?
Yes, of course, Daniel. Thank you very much for your introduction. So my name is Dominik, and I'm currently doing my PhD at the Technical University of Dresden. And I'm pretty much investigating how to analyze textual data that has a geospatial reference attached to it. And we're developing different algorithms around this, and we're trying different things like how we can best explore the data and how we can put it best on a map. And back then in Florence, when we met at the Phosphor-G, back then we used an algorithm called hyperloglog to analyze social media data. And the way this algorithm worked is a little fascinating, I would say, because you can count so-called cardinalities that basically mean the distinct numbers of, for example, social media users that posted something on social media about a certain topic. For example, if back then we analyzed urban green spaces. So if a user talked, for example, about trees, about grass, about bushes, about flowers, this could, for example, be one topic that we were interested in. And what we did is we counted the number of distinct users at a certain urban green park, for example. And in this way, we could quickly understand which park, for example, had the most users and how users used the park. For example, there's a nice framework called Cultural Ecosystem Services to understand what users are actually doing in these parks. Are they socializing? Are they eating food? Are they studying? Or are they playing sports? There are many different things that you can do in these parks. And the way this algorithm worked and the way we did our research back then was that we created these so-called hyperloglog sets that we could use by minimizing the detrimental privacy effects that any kind of analysis of social media could, of course, have for the users. But we could still grasp the idea of how users would make use of these urban spaces, because this is quite a balancing act here, because there's a lot of ethics involved in there. And we really kept an eye and our focus on keeping the users' privacy, but still having something to analyze. And this is the balancing act that we found ourselves in. But of course, back then, we were just analyzing very coarse topics. So for example, nature was one topic, or sunrise, sunset could be one topic, or sports could be one topic. So we needed to know beforehand what we were actually looking at. And this is okay if you already know what you are looking for, or if you have local stakeholders, like, for example, back then I was analyzing the city of Bonn and I was in touch with all people. I also studied there. So I had already some kind of understanding of how the city worked and what things were most important in the city. So I already had an idea what we could analyze. For example, the cherry blossom in Bonn is important. Beethoven was born there. So those were like some kind of topics that we were interested in. But what if you don't know that some things are important for a city? What do you do then? You cannot identify a list of keywords for a certain topic that you're not aware of course, because you just don't know the keywords. So you cannot see anything in the data that you're not aware of beforehand. And this is the reason why I moved on in my research and I developed a different strategy.
Can I just stop you there just for a second? Not that I don't want to hear about the different strategy. We're going to get there. I just want to make sure that people understand what social media data is. So, I mean, they probably have a good idea of what social media is, but tell us more about this data. Help us understand it. In my mind, it's very unstructured data.
Oh, yes, it is. Or it depends on the perspective. If you look at the way that, for example, Instagram or Flickr or Twitter, how these platforms work, they just exchange the data in a structure called JSON. And JSON is inherently structured. You have different nodes. For example, there would be one node about the text, about the caption that a user uses when someone is posting something. For example, today I'm having a great time at this park, and then posting a picture. And there is, of course, also a date time referenced, and there's also a location attached to it. For example, Instagram does really nudge users to add a geospatial reference to their posts. On Twitter, it's a little more hidden, and on Flickr, you can also do so. So the way we can think about social media data is actually pretty simple. So you have some kind of text, some kind of image maybe, some kind of geospatial reference, and the easiest way, just a pair of lat long, and maybe a date time. What we are interested now in our research, just to put it very simply, we have a text and we have the geospatial reference. And this is how we can analyze the data. And of course, text is very hard to process for computers because computers do not think in letters, in characters, they just think in zeros and ones. So we need to find a way to make computers understand what we're talking about and to analyze the data. And this is where the magic comes into play. And this is where this episode will evolve around, like around transformers, about deep learning models, and so-called embeddings. And embeddings is where the magic happens. Because we can use so-called embeddings, which are nothing else but the numerical representation of any kind of input data. The input data can be, in our example, just be a piece of text, like the caption that a user used to post on social media. For example, having a great time at this nice park would be the input data. Then we can use a deep learning model and convert this text to the numerical representation. And you can think of this numerical representation just as a vector of numbers. And a vector is nothing else but a list of numbers. This can be zeros and ones. This can be float numbers. It's just a different form of representing this input data.
And would it be fair to describe that this vector as, or these list of numbers as dimensions? Each number representing a dimension?
Yes, exactly. This is a very easy way to understand these kind of embeddings. For example, you could think of these dimensions of having a certain meaning. So what a deep learning model could do, for example, is just count the number of legs of something. For example, I'm a human, I have 2 legs. If the model sees a dog, it has 4 legs. So if it sees a centipede, you could have the number 1000, for example. And the first dimension of one vector could, for example, be the number of legs. But these dimensions, they can also represent more complex things, like not only like physical things that you can imagine, but they can also represent, for example, an attitude, like is there like a positive vibe or like a more negative vibe? Or they can represent also more complex meanings of a sentence or of a caption. So these vectors, they are great at grasping the meaning of something instead of just looking at the keywords that do occur in the caption. And this is a great advantage and the great development of, let's say, the recent 2 years. There's so much happening. Like these algorithms, these deep learning models, they become better and better at really capturing the meaning of the input data. And this is the beauty. You can just boil down any kind of input text, might it be one word or a sentence or a paragraph or even an entire document or a whole library of things. You can boil it down to a fixed number of numbers, to one vector, to one embedding. And this is where the actual magic comes into play, because then you can use these embeddings and perform a similarity calculation. And the way you can understand the similarity calculation is very easy. Just imagine 2 points in space. you have 2 points, and then you just you draw the line to the point of origin. Then you have 2 lines, 2 vectors, and you have some kind of angle between them. And this angle is something that we can use to calculate the so-called cosine distance. And this distance is telling you something about the similarity of these 2 embeddings and respectively about the 2 texts that you wanted to compare to each other. For example, you could have one user query, like in our example, we wanted to create a search engine that was capable of giving the user the freedom to enter any kind of search query. Like, for example, I'm interested in any kind of sports. So the user would just input sports. And on the other side, we have a large database of social media posts that, if you remember, they just consist of the text in our example and one vector. So you can run this user query against the whole database of vectors, and then you would just end up with the distances. Like, how distance is my user query to all of these 1,000 posts, for example. And then you can simply rank them by the distance. And then on top, you would have the most similar posts. And on the bottom, you would have the less relevant, the less similar posts, for example.
I just want to make sure, before we move on, I just want to make sure that everybody is following along here, because we've jumped in really deep, which is fantastic, because I'm really enjoying this. But right at the start, we talked about using this hyperloglog, and we talked about needing to define the topics of interest before we started our analysis, because that is the way we looked for these topics when we were processing the data. And what you're saying is you don't have to define topics that you might be interested in analyzing later on. All you need is this coordinate, a geographic location or a geographic reference, and the text, and you turn the text into an embedding, meaning that you can run queries against a database of these embeddings later on without needing any sort of prior knowledge of topics that you might be interested in searching for or analyzing. Is that correct?
Yeah, that is pretty correct. So the main advantage over also doing like a full text search, for example, is that you can capture the meaning of any kind of input data. So you have this whole database of embeddings holding really the meaning of the text that you see on social media. And you do not need to know anything in advance about these embeddings, because the embeddings, they condense all this information in themselves. Even if it's maybe a little hard to understand that these embeddings that all have a fixed length can really accurately represent the input data, this is what they are doing. And so if you represent this data as embeddings, you do not need to know anything in advance about the data. You just create these embeddings, and then you can run any query against it. And because the way these deep learning models work is that they are trained on very large corpuses of data. For example, the whole internet, all of Reddit, all of Wikipedia. This is a lot of text. And so these deep learning models, they are pretty good at capturing the meaning of basically anything. So of course, if it becomes a bit more niche, like if you're diving into some particular research, for example, these embedding models, they're usually very generalized models to capture like the overall meaning of any kind of text. So they might not be aware of your particular research niche. So they might not be great at capturing those kind of details, but they're doing an amazing job of working with our everyday language. And so is our language on social media usually. This is our everyday language that we use because we want to make other people understand what we're talking about. And so these models do a great job of capturing the meaning that we transport in these posts. And then we can just run any kind of query against that. And as you summed up perfectly, is that then we end up with this database of the similarities. For example, a similarity can just be a score between 0 and 1 on the one hand. And on the other side, we do have the geospatial reference. So what we end up with is just a long number of coordinates that have some kind of similarity score. And then we can put it on a map, of course. The most or the easiest way of doing that would be just to plot a number of points on the map and color them, of course, based on the similarity score. This would be the easiest way of representing this data spatially.
Okay, so that was a great explanation. We're going to get more into the weeds in just a second. Perhaps you could give us an example of, tell me what's possible now. You've got this database full of a lot of vectorized social media posts. Give me an example, or perhaps multiple examples of what I can do. Like, can I just search? Is it just search for any word? Can I search for? Is it searching for words? Can I use a sentence? Like, show me all the people that are say this specific thing, like this thing, are positive, are feeling sad. Are these the kinds of things that are possible now?
Yes, you can do many different things. You can search for emotions. You can search for also individual words if you like, but you can also, your query can also consist of an entire sentence. For example, this could be enjoying my book at this urban green park. And you don't even need to mention reading, but as the embeddings, they capture the meaning of the text. It would also capture if someone would just post something about reading and without even mentioning a book or something. So the similarity here would be very high because having or enjoying my book at this urban green park is very similar to reading something laying down on the grass, for example. The meaning is almost the same, but they don't use the same words. So cuisine distance is great at capturing the meaning and at paraphrasing sentences. And the beauty is that you can do both. You can also look for words. Like if your query would just be sports and someone posted something or just the word sports, for example, this would be a similarity of 1, like 100%, because the vector would be identical. And if you have the identical vector, then the similarity is, of course, the same, basically. But if you have someone posting something about football or tennis, then the similarity is still very high, but it's not 100%. It might be like 90%, for example. But it would also capture some, like 2 guys maybe playing with a ball and tossing around the ball in the park. This would also be some kind of sports because the model does understand that this is referring to some kind of sports related activity. So you can look for anything in the data. And as you could also look for these kind of emotions, emotions are very subjective. Like emotions are not really objective because they might have different meanings for everyone. For example, of course, if you look for like having a great time, then it would find like very positive emotions. But as we all do perceive space differently, sometimes your interpretation of some kind of text might be different than mine, for example. I will give you a very, very haptic example. For example, if in the middle of the night, you would have a group of young people partying at the central station, for example, this could be positive for you because if you're young and if you enjoy like party and if you're very outgoing and you want to socialize, okay, great, they're having a great time. You know, I want to go there. I want to be in the middle of life. But for other people that maybe try to avoid this because they might perceive it as a threat, as danger, they might avoid this. And so you need to be a bit careful of what you put in there because the model is itself just trained on lots of training data. And so to say, in a very certain way, this model is objective. So you need to explain what you're referring to.
Does that take a little bit of time to get used to writing those queries? Because keyword search is very straightforward. Show me every sentence that mentions this keyword, and then you could think about regular expressions, for example, like I want to get this stuff out of the data set. But it sounds like there's a lot of experimentation involved here. How does the model perceive this emotion or this particular situation?
Yes, there is a certain time that you need to get used to these queries, unless you're looking for very simple phenomena. Like when you look for like physical things, this is still straightforward. You can just describe what you're looking for, like a tall building or like an urban green park. This is very straightforward. But once you get started with it, and if you look for like very abstract concepts, like for melancholia, for example, or for nostalgia, like you would need to know what you would expect the model to return. Like you would need to have some kind of idea. Like these concepts are very general. And of course, or the way that most users do interact with these kind of databases, and the way I also found myself interacting with it and searching things in this, is that I was iterating a lot. For example, in the beginning, I was just interested in, for example, how people would perceive the space. So I would input emotions. Yeah, like for example, melancholia or just like feeling great today, like happiness or also sadness. You can input these emotions and just have a look at the results. Like what is actually very similar to these things. And then you would already get some kind of idea about these databases and about the posts, what the model could potentially return. And then you can, of course, narrow it down. Maybe you're interested only in, I don't know, sad students that are obliged to study even though the sun is shining. So, like this kind of sadness is a particular kind of sadness that is like a bit ironic, You would like to do other things in the park than like reading a book and studying. But you would understand these very similar, this very interesting things also in relation to the time, like when you look at these posts. If you look at these posts in summer, of course, like people tend to be outside. If you look at these posts in winter, people tend to be sad at home, maybe. And this is the kind of things that you can understand very easily when you query these databases.
Okay, I'm hooked. This sounds like a brilliant idea. Maybe you could give us an idea of how you created this database. My understanding is it involves something called transformers.js.
Exactly. This is what you can use. I mean, transformers is just the typology of the architecture that we have now. This is, let's say, the latest state-of-the-art architecture that we do have to create these so-called deep learning models. And there are different typologies. There is like a plethora of models available online that you can simply download and run on your computer as well. And this is where transformers.js is doing a fantastic job, because you can just run almost any kind of model on your phone, on your computer, even without GPU, and create these embeddings. You can do this in your browser if you like to. You do not need to be GPU rich. You don't need to have these super expensive setups with multiple GPUs that cost like tens of thousands of dollars or so. You can do this in your browser. And this is the magic. This is what fascinated me. So what I did, for example, with this database of social media posts, I just calculated the embeddings all on my computer. And I don't even have a GPU. So maybe I need to wait like a bit longer because the CPU is doing a poorer job than a GPU would do. But this still works in a fairly like quick time. Like you can generate, I don't know, like 20 or 30 or 40 embeddings on my really old CPU per second. And this is actually enough to encode this once. And then you have this database. Like you would do this only once if, for example, you scraped the data for a whole city, like for, I don't know, like 1 million social media posts, for example. You do this once. So then you end up with this database of the embeddings and the geospatial reference on the one side. You only do this once. And at the moment, I'm writing a paper about this demo that I created, where the moment a user inputs a query on this web app, the embedding is created in the browser, because otherwise I would need to have some kind of expensive service running on my server, and I don't want to do that. So I just shift the workload to the browser because I just need to create one embedding. This is like a very little amount of work for the CPU, and it's done in the fraction of a second. Like, for example, in 100 milliseconds, you have one embedding. And this is enough, because when a user inputs a query, then you calculate the embedding on the fly, and you can just compare this embedding that you just calculated to my pre-calculated embeddings of the whole database. And this is what you can do in the browser. You don't even need to have like some expensive server. GitHub Pages is enough to host this. And you can have these very powerful applications that before were only possible of having like complex setups of Elasticsearch, fuzzy search, and many complicated things of looking at duplets and triplets of words. There is a whole research field dedicated to analyzing text. And now what you can do with like very little resources, we leverage these deep learning models that are so great at capturing this meaning. And we can create these web applications in a day or so.
Wow. Hey, like earlier on in the conversation, we talked about this idea of dimensions and thinking of and embedding a vector as a long list of numbers, of dimensions. And you gave a few examples of what these dimensions could be. Do you decide this when you create these embeddings? Do you say, I want this embedding, this vector to have X number of dimensions? How does it like, or is it dimensions? Are they always this many?
So it depends on the model that you're using. Usually, or the way it was until a couple of months ago, because the development is just so rapid that you can barely keep up with what's going on. But the way it was until a couple of months ago is that one trained deep learning model would output always a vector of a fixed length. And with a fixed length, I just mean, for example, 384 dimensions or 800 dimensions or 1000 dimensions. It's always a fixed length of numbers in this vector. And depending on the model that you use, also depending on the size and the quality of the model, these vectors are larger or smaller. For example, there are great models that are able to capture the meaning of a sentence in only, let's say like 384 dimensions, which is pretty small for a vector. But then there are these larger models that use, for example, 4,192 dimensions, or even larger ones like GPT models that are really huge in size, and maybe they use like 16,000 dimensions. So they have like a really broad way of capturing meaning in many dimensions. Of course, like the more dimensions you have, the more meaning you might be able to capture. But the longer this vector gets, the harder it becomes to handle. Because if you think about it, if you have just one tiny word, like the word sports, then you do not want to end up with a vector of 16,000 dimensions that consumes a huge amount of memory. Like it's a huge footprint that you need to deal with. And if you look at 1 million posts, then 1 million posts multiplied by 16,000 numbers, this is a very large amount of gigabytes that you would need to handle this database, even though you just have a few strings in there. And so you always want to try to keep the vectors as short as possible, but as long as needed to still capture the meaning. And if you're new to this, it's really interesting to take a look at the massive text embedding leaderboard. This is where all the open source models are tested and run against each other. And you can have a look at the leading models. I mean, there are the really big ones like Claude, Opus, like GPT, Command R. There are different models there that have very large dimensions. But very close to the top, you see like really small models that only have like 300 or 400 or 500 dimensions, and they work great. They work almost as good as these super large vectors. And right now there's something else that happened because there are new architectures, of course, and there is something called quantization. There is something called the binary quantization, and something very fantastic that is called matryoshka embeddings. So this is a way where you can actually reduce the size of the vectors flexibly without losing too much of the capacity of capturing the meaning of the embeddings. So you can decide yourself, how long do I want my embedding to be? Do I want it to be like 1,000 dimensions or just 200? So you can decide yourself how many dimensions you want. But of course, you always need to stick to the same number of dimensions if you want to calculate the cosine distance, for example.
I think that's really interesting that the last thing you said, that the vectors in your database need to be the same size as the vector that you're using as a query. At least that's the way I understood it. Is that correct?
Mm-hmm. Yes, that's correct.
That's interesting because I was thinking, I guess you could use different length vectors to represent, I don't know, maybe more complicated sentences or complicated words that have many different meanings or many different ways of interpreting them. But if you did that, then I guess you'd run the risk of not having the same size vectors on each side of the equation when it came time to query the database.
What you can do, and this is pretty much what you proposed, is that you create vectors of different lengths for the same query. So one time you decide maybe to use the smallest model available just to have a smaller memory footprint of just 300 dimensions. But then at the same time, you also calculate the largest vector possible, like of 2000 numbers, for example, in the vector. You can do both and have like two vectors. And then you can decide yourself, okay, do we have maybe a more powerful machine that is maybe so powerful that you can use the larger model and the larger embedding? Or do I have like a smaller machine and I just use the less powerful model that is like slightly less accurate at capturing the meaning, but is still doing a fantastic job? In my experience, as long as you stick to the leading models on this leaderboard, you cannot really do anything wrong. These models, they are performing really well, and they're just nuances where they vary in quality. So you can be pretty sure if you use the latest, also smallish kind of models, they do a fantastic job at capturing the meaning. And only if you need really the absolutely highest accuracy, then you, of course, you would need to have some kind of GPU or so.
It sounds like the law of diminishing returns also applies to the models.
It depends. There is a limit to the top. Like you cannot say, okay, now I want to create an embedding of 1 million dimensions. Because at a certain level, you have too many dimensions. So you don't get any extra benefit of adding more dimensions. Because the way these dimensions work is a little abstract. So you cannot adhere to the example I gave you earlier, like how many legs does a human have? How many legs does a dog have, for example? These dimensions, they don't represent one specific feature anymore. They are abstract. And the reason why that is because these models, they produce so-called dense embeddings. And dense means that they are condensed to less dimensions. And so it might be that one dimension in the vector might represent multiple features. Or maybe the first 3 dimensions, they are acting together in some kind of way to represent some kind of meaning. So you cannot easily say what kind of dimensions are good for one specific topic. But you can be sure also if you condense the vector even further to just 200 dimensions, for example, that even if you condense them, they still capture the meaning really well, especially for very generalistic kind of terms or queries. But yes, in general, you have this, or you do apply this law, like the smaller it gets, if you just have 2 dimensions, of course, then you cannot represent anything anymore. But if you have 1 million dimensions, then you don't have any extra bit benefit there.
Can you talk to me about something called a chunking strategy, please?
Yes, of course. That's something that is relevant if you maybe go to a more abstract level. Like I initially started with analyzing social media data, and social media data is inherently short. You have very short posts, and they always fit in the so-called context length of these embedding models. Because embedding models, they have some kind of fixed input length that you can give to them, and they will give you an embedding back. But of course, if I input 1000 PDF pages, an embedding model might not be able to handle them anymore. Like it's just too big. So we need to find a strategy to also use very large texts and hand it over to the embedding models. And this might be the case, for example, if you take a look at Wikipedia articles. Wikipedia articles sometimes even have a geospatial reference. For example, the article about the city of Berlin has a geospatial reference, or other cities might have it. But the problem with Wikipedia articles, especially about the city of Berlin, for example, is that they're pretty long. So they're really long input sequences. And this is where these chunking strategies come into play. So what we can do here is that instead of handing over the entire text to the embedding model, we just chunk it in smaller parts. And the way we do this is a whole philosophy for itself. Like if you look at Wikipedia articles, it's easy to imagine that you have different paragraphs that talk about different things. And there you already have some kind of structure that you could use to chunk these long texts. For example, just split it by headings. Or if the text is still too long, just split by paragraphs in the larger paragraphs, for example. You can do that. But if you have a very long text, like a report about something where you don't have any headings, any given semantic structure that you could use to chunk this text, you can just chunk it by fixed length, for example. You can say, okay, I just want to chunk it by 300 words, and then I just do the cutoff. But then, of course, you would run the risk of splitting up sentences, and then you lose the meaning. Like if you cut the sentence at the wrong place, you lose the meaning, and it becomes a bit fuzzy. So you want to try to chunk a text semantically. And that means that you want to have semantically coherent passages and give these coherent passages to the embedding model. So for example, if you chunk one text into 100 chunks, then you hand over every individual chunk to the embedding model, and the embedding model responds to you with one embedding per chunk. And what you can do then is you average all the embeddings, and you get one averaged embedding back. So you just go from 100 embeddings to one embedding only. And then you have a sort of like high-level embedding that represents the meaning of all of the text. This is what you can do if the text becomes too large that you cannot give it to the embedding model anymore.
In a roundabout way, this reminds me of a tiling strategy for large images.
Yes, this is actually pretty similar. Like when you think of like rivers or buildings or urban green parks, if you look at tiles, there might be certain semantic units in there. That's actually right. It's very similar, and there are many analogies between, for example, Earth observation data, like satellite data, and these chunking strategies. In the end, it all boils down to just looking at certain input features and creating an embedding for them. There's also something called semantic chunking, where you would apply a complex heuristic of calculating embeddings with a sliding window. So just to see where the embeddings have the greatest difference to each other. This is also what you could do, of course.
Wow, man, I have a lot to learn. I can tell you that. We've come a long way. We've come a long way in the conversation, and you've been brilliant. Like slowly but surely breaking this down and helping me, and I'm sure a lot of other people understand it. But let's come up for air just for a second here. And let's think about what you've done. So you've taken a bunch of, I know you term it as structured data because you're talking about these social media posts is living in a JSON format, which is, has a structure to it. But the text itself within that, it is unstructured. It could be anything in there. And so you figured out a way of creating a representation of this, embedding a vector of this. And this means that we can search against this database of vectors, of embeddings, without having sort of predefined ideas of topics that we're going to look for. We can just grab this data, embed it, and we're left with a coordinate and a vector of it, and then search against these vectors, which sounds amazing. Is this going to replace SQL, these structured databases? Like, I guess I know what your answer is going to be, but can you give me an idea of when I should be using this and when I should be using, a structured database?
That's a pretty good question, actually. So just to give you the answer, no, it won't replace simple SQL queries. That's a definite no here, because you still need to make sure that certain keywords are maybe in some kind of text. So you want to be sure that something is in there. And the problem is also with these embedding models that it becomes kind of fuzzy. So it becomes kind of a black box, and it's not as explainable anymore as if you look for keywords, because then you have just true or false. The keyword is in the text or is not. Then you know for sure that this is relevant to you or is not relevant to you. And on the other hand, you have these embeddings that give you some kind of fuzzy score between 0 and 1. So to respond to your question is when you're looking for something that is slightly more fuzzy, or if you want to do data exploration, embeddings do a fantastic job. On the other hand, if you want to have really binary results, does a keyword occur in a text or not, then you would use simple SQL queries and look for certain keywords, for example. You can, of course, also combine them. Then just start with the embeddings, explore the data, see what kind of keywords are ranking highest, and then look for these keywords. So it can be, it's not like black and white here. You can use both and combine them. And what matters is that in the end, you get better results, of course.
How do you deal with this explainability problem that you're talking about? Because at the end of the day, it is a black box. If you're doing analysis on this data, and I know you are, how do you build explainability into that? How do you like save the query that you use? Do you save a copy of the data of the database, give people access to it? Are we heading down that sort of the path of a reproducible research, or is there something else?
So the easiest way to do that would if we leave privacy completely apart. If we would persist the whole database that we, for example, mine from any kind of social media platform, then we would still have the raw data, like, the string that a user posted on social media. And you would see this attached to the similarity. Okay, here is the user X that posted something about the urban green park, and the original text is this or that. Then you would have an immediate overview over what people said, and you could immediately verify against it. In our case, we cannot do this because we do not save the raw data, because this would really heavily inflict the user's privacy. And this would be something called data retention that we want to avoid as much as possible. Like, this is very bad for privacy. There's also something called geoprivacy, because geoprivacy is very important to users because you can trace back users very easily if you look at, for example, the daily geospatial behavior. But let's not go too far in this direction.
If I understood you correctly, you're saying that, okay, if you wanted to prove the results that we're getting, based on these queries, you would part of the database would be the original piece of text. You would persist that, you would save that on the disk. You would search against the embeddings, and then when the embedding come up, you say, okay, well, in that, this is what the model is telling me. This is what the representation looks like, and the exact piece of text is there, and make a comparison and use it as a ground truth.
Yes. So what you can do is that you just compare it not to the individual user's post, but you just take a look at, in the case of Instagram, for example, you take a look at the location where someone posted something about this. Because there's a high probability that also other users might post something about the same phenomenon. Like if in one urban green park people tend to play football, I don't care about the individual user who posted something about football. I just care that people overall do play football there. And the way we can do this is that we can just save some kind of abstraction of the geolocation, and then again use the social media platform to verify against that. So we would just take a look at the Instagram location and have a look at the most recent posts. And then there's a high probability that we would see some people doing something similar in this park. So we can sort of verify that. But it's, of course, a little more complicated than keyword-based search, where you have this certainty about something.
What about, so you mentioned Instagram. Instagram also has images. Can we use images to help verify what's happening in the text, or vice versa?
Yes, we can. And this is the beauty about these embeddings, because there are two more things here that are wonderful, because you can not only use text, you can also use imagery, or you can use videos or audio tracks, or any kind of input data that you can possibly imagine, and convert it to these embeddings. So this is a methodology that is super flexible. If we think about a simple web application, it doesn't matter what the input data is. It just matters that we get these embeddings and that we can query against these embeddings. So what we could do is we could also create the image embeddings and then ask the database, hey, what is most similar to these images, for example? You could do the same. And something that is also wonderful about this is that we have multilingual embeddings. So you can query in one language, like I could query, for example, in German against an English database. Or you could query in English against a German database, or vice versa.
Wow, that's really interesting when you think about scraping social media, for example. You don't need to, I mean, you could try and sort of limit it by a geographic area and say, we're assuming that most of the posts we're going to get here, most of the data we're going to get when we scrape Denmark is going to be in Danish. But it's not always going to be true, because there'll be other people there that don't speak Danish. So you'll get other languages in there, but it doesn't matter if you have a multilingual embedding.
Exactly, that's right. And social media posts inherently are super mixed. Like I can see this in German, users tend to use English hashtags, but with German mixed up. Then you have lots of tourists, of course, that come to your city and that might even use different languages like Spanish, French, or Chinese, or anything. And these models, they're great at creating embeddings for any kind of language, and also for these like mixed languages.
Is there a world where you could use the text to create an image? Where, in the world of generative AI, could we do that as well? And then see, does this image like match? Does another model agree with the text, essentially? Looking for some sort of proof that this is what they were talking about?
This is spinning the idea even further. Like when you have one embedding at a certain location and you want to know what this embedding is about, there is a way to go back from the embedding to the primary data. Of course, you never have like 100% certainty about it, but you can recreate some kind of input. So what Google, for example, just did is release one research paper, and they managed to reconstruct embeddings or the input data that was given to these embeddings. And you could do the same for imagery or for videos. So we're not yet there, but this is absolutely doable. So you can basically reverse these models, and then you could just take a look at the most similar embeddings for one location and create like some kind of image of the location that is summarizing what people are doing there, for example. Like one green park with people reading books, sad people studying, or, doing sports, eating. And you could really create these kind of like summarizing imagery.
But what does that mean, being able to recreate the original input from embeddings? What does that mean for privacy?
This is a bit tricky, because if you have the embeddings, it doesn't mean that I cannot recreate the original input. Actually, I can do that if I have the exact embedding. And this is where we are still doing research, trying to understand how much we need to compress these vectors, or how inaccurate they need to be, so that these embeddings become so coarse that you could not really reconstruct one particular social media post on the one side, but on the other side, you want to still be able to have a sufficient number of dimensions in your vector that you can still query against something that is meaningful, that you can actually still work with this. And this is, again, some kind of balancing act. What I personally found is if you reduce the accuracy and if you, for example, concat, for example, or if you just average two dimensions with each other and you reduce the number of dimensions, you generally still get really good results. But of course, you lose a lot of power to reconstruct the original data. So this is good for privacy and just slightly lowering the quality of the cuisine distance function that we have there. So there is still some kind of balancing act there. And this is still some active research going on. But let me just be clear. Embeddings do not preserve your privacy yet.
I appreciate you making that very clear for myself and for the people listening. How do you keep on top of all this? Like, I realize this is part of your job is to research this, but where are you getting your information? Where are you? Who are you following? How do you keep up with all of this?
So what I really like to do is to follow what's going on Hugging Face. This is a platform like GitHub for everyone that is interested in AI, basically. So you can just look at, for example, the most or the best performing models, for example, that create embeddings. You can take a look at the leading models that can generate text. You can dive into these communities that are training models, and you can see what kind of input data they use, what kind of architecture they use. So there's many places where you can inform yourself. Good starting point is just to follow like some stuff from Hugging Face because they would periodically repost things of the latest research teams, like what they are developing. But of course, like the development is so rapid that you can, of course, also develop this kind of fear of missing out that you need to stay tuned every day. And this is actually true. Every day something is released. So yeah, don't let yourself be stressed. I think if you have a high level overview of how these things work, and if you maybe did like a very small example yourself, if you coded it, and if you see that you can get back one embedding and you calculated the similarity once, then you will realize the potential of applications for this. And this is the moment where, or this is the most important thing that you take away should be probably.
We mentioned transformers.js earlier on in the conversation. Is this, if I'm trying to get started with this and want to create my own sort of test database, is this the best place for me to start, or should I go somewhere else?
I think transformers.js is a great starting point because they have amazing demos online. You can just use it in your browser. So everything is happening in your browser, on your computer, privately, so you can test anything. And transformers.js is doing a great job at employing different models. So not only for creating embeddings, but they also have like ready applications that you can use where you can just hand over certain terms and add a query. And then it would give you back the similarity of these terms, like what is the most related term to my user query. Or it can generate audio for you. The latest one is that you can generate music from it. You can upscale images. You can generate text in your browser. You can do everything there. And this is an amazing playground if you just want to have an idea of what is possible nowadays.
I think I will include a link to that in the show notes because that sounds amazing. I'm going to spend some time there myself. Dominik, thank you very much for your time. I really, really, really enjoyed this conversation. I enjoyed talking with you back in Florence. I've enjoyed our pre-interview as well. I learned a lot during that, but I've even learned more during this conversation. So thank you so much for your time. It's been great. Where can people go? If they want to have a look at some of the work that you're doing, if they want to reach out to you personally, where can they do that?
Of course, just go maybe to LinkedIn and follow me, or on Twitter, or even on my personal homepage on geo.rocks. There you can follow my latest work. I will try to publish a bit more blog posts maybe in the future to keep up with everything.
Great. I'll put links to all those places in the show notes, and I hope that people will take the time to follow along. Thank you very much for your time. You have been awesome. Cheers.
Thank you very much, Daniel. Goodbye.
Really hope you enjoyed that episode with Dominik Weckmüller, researcher at the Technical University of Dresden. There'll be a few links in the show notes today so you can connect with Dominik if you want to learn more. I'll also have a link to Hugging Face, This is one of the resources that he mentioned towards the end of the conversation, and I spent a bit of time there myself, and it's really helpful, really interesting. Also, there's something called Spaces there, so click on the Spaces button and you can explore a bunch of apps that people have published on this website. It's almost overwhelming how many there are. So, but please take the time to check it out. I also have a link to the new project that I'm working on, Quick Map Tools. Again, it's a work in progress. The idea here is to build out a set of helpful browser-based map tools. And if you do take the time to check it out, I would love some feedback. It would be really great to hear what you think. And maybe if you have any suggestions, that would also be much appreciated. Well, thank you very much for listening all the way to the end. It's much appreciated. I'll be back again soon. I hope that you take the time to join me there.